So yeah, we'll talk about massively parallel algorithms for counting small subgraphs in a given input graph. And this is joint work with Talia, Kwan, Slobodan, and Ronit. So the massively parallel computation model is motivated by real-world parallel systems which use these distributed clusters of many different machines, where the machines can communicate with each other via sort of rounds of communication. And the reason for doing this is that the input might not fit into, or even the output might not fit into a single machine, so that it's distributed across multiple machines, and each machine has limited space to store the input. And this is supposed to be the theoretical framework for studying real-world parallel systems such as MapReduce, Hadoop, Spark, etc. There has been a significant amount of work in graph algorithms and MPC model over the past few years, including many different combinatorial problems like matching, MIS, vertex cover, coloring, as well as notions of graph sparsification, connectivity, etc. But first, let's start with a definition of the MPC model. So generally, we will have a collection of M machines, where each machine has a small amount of space S, which is not sufficient to store the entire input. So for instance, if the input is a graph, all the edges, or maybe not even all the vertices, can be stored on the same machine, but instead they will be distributed across multiple machines in some arbitrary fashion. And since no machine, and the total space will be M times S, and since no machine actually knows the entire input, they have to communicate with each other in order to figure out the correct answer. And this generally proceeds through synchronous rounds of communication, where after doing a certain amount of computation, the machines are allowed to exchange data with each other. Generally, the amount of computation that happens between the rounds is assumed to be unbounded, and the main bottleneck is supposed to be the actual communication number of rounds, and that's what's going to be our notion of time complexity in this model. So there's three different regimes we'll talk about when talking about MPC algorithms. The first being when the space per machine is strongly sublinear. So for example, specifically in the case of graphs, it means that now the space per machine is going to be sublinear in the number of vertices, so you can't even store all the vertices in a single machine. Then there's also the near linear memory regime, where the space per machine is enough to store all the vertices, and potentially you can even have some additional multiplicative polylogarithmic factors, and this creates a second regime. And the third regime is going to be the superlinear memory regime, where the space per machine is sort of superlinear in the number of vertices, yet still sublinear in the number of edges of the graph. And generally, we will want our algorithms to be quite fast in this model because we're just looking at the number of rounds. So specifically, we might want something like log n rounds of communication, or ideally even a constant number of rounds of communication. We would also like the total space, so the number of machines multiplied by the space per machine. This total space should not be too much larger than the input. So generally, we will try to get algorithms which are tight with the size of the input in terms of total space, but may have some additional polylog factors. So the results in this presentation are going to be twofold. First, we'll present an exact triangle counting algorithm for the strongly sublinear memory regime. And in this setting, we are going to assume that the graph has bounded arboricity, and we'll get into what that means in a bit. But given that the arboricity is alpha, we're going to use an alpha factor additional space, which is generally okay, assuming the arboricity is small, which happens for many classes of real-world graphs. And this algorithm will take only log n rounds to give us an exact triangle count. And in the near linear memory regime, we obtain a different algorithm, which is an approximate triangle counting algorithm. And this has a slightly different assumption, where it assumes that the number of triangles is at least the square root of the average degree. And since this is an estimation-based algorithm, and it gives us an 1 plus epsilon approximation to the actual count, that sort of maybe is an intuitive reason for why we need a lower bound of the number of triangles, since we're looking for a multiplicative approximation. So there's very few triangles, it might just be impossible to find it. So distinguishing between 0 and 1 will throw the approximation off completely. And this algorithm only takes a constant number of rounds and actually uses an amount of space that is tight with the size of the input. Furthermore, in our paper, we also extend both of these results to counting general cliques of constant size, as well as counting, the exact counting algorithm can be extended to counting small subgraphs of size at most 5 using a later result that was presented in ITCS. We also provide some simulations in our paper where we find improvements in real-world graphs for both the round complexity as well as the approximation ratio. But first, let's start with the exact triangle counting algorithm. So we can contrast our algorithm for exact triangle counting with some older algorithms in the same model. For example, let's first start with what we mean by this bounded arboricity thing. So the arboricity of a graph is this number alpha such that you can partition the edges of the input graph into alpha different sets, where each set is by itself a forest. And if you can do that, that means the arboricity is at most alpha. So alpha is the minimal number of forests that can totally cover our graph. And the reason that we're interested in this metric is because real-world graphs tend to have arboricity that's quite low, and theoretically we can sort of take this to be something like polylog n. So given that, we can compare to one of the first algorithms for counting triangles in MapReduce, which uses an overhead in the total space of some variable parameter, let's say rho, and gains some ground by rho square in the space per machine, and their algorithm works in a constant number of rounds. So compared to our algorithm, they actually get a much better number of rounds, but as long as the arboricity alpha is bounded away from its maximum value of square root of m, so if it's polynomially bounded away from its maximal value, we actually get both better space per machine and total space. Next, we can compare to an algorithm by Chu and Cheng, where we get a worse bound for the total space because they actually are tight with the size of the input. However, their space per machine is in the linear regime, and the number of rounds they use is much larger at O of n. And finally, we can compare to the algorithm that is perhaps most similar to ours, which is the sort of folklore algorithm of Chiba and Shiseki. It's not meant for MPC, but can be easily adapted. And they obtain the same total space as us, and in some cases, they even get better space per machine bound when alpha is small, but our number of rounds is exponentially faster at log n instead of log n. So that's the comparison to sort of past work for exact triangle counting. One thing to note is that our algorithm actually works in the strictly sublinear setting, regardless of the arboricity, and this is a formal statement of our algorithm for exact counting, which uses log n rounds, m alpha total space, and sublinear memory. But let's first start with the original sequential algorithm of Chiba and Shiseki, which can easily be converted to an MPC algorithm that, however, works in log n rounds. So the main idea in this algorithm is that given an arboricity alpha, we are going to successively delete vertices with degree less than 2 alpha. So for instance, these green vertices, which have low degree, get deleted from the graph. But before we delete them, we count all the triangles that are adjacent to them and sort of count them and add them to the total count, and then we delete them. And since the remaining graph is a subgraph of the original graph, and the arboricity is basically a covering of forests, we note that the arboricity in the final graph still remains at most the original value because the old forest can just be sort of restricted to the new vertices, and we still obtain a covering of forests. So the new graph has the same arboricity, so we can just repeat this procedure over and over again. So we again look at the low degree vertices, we count the triangles next to them, we delete them, and eventually we get rid of the entire graph. And what this does is that it reduces the number of vertices at each step. Specifically, if we look at the number of edges that are in the graph initially, which is m, that is at most n times the arboricity. And the number of vertices remaining can then be bounded because note that the remaining vertices all have high degree in the original graph. So they've all degree at most, or at least 2 alpha. Therefore, there cannot be too many of them because if there are more than n over 2 of these high degree vertices, that would sort of contradict the upper bound of the number of edges. So if you had more than n over 2 vertices and each of them has degree at least 2 alpha, that would mean that there is more than m edges in the original graph, which is not possible. Therefore, the remaining number of vertices has to be at most half the original number. And since we do this successively, the number of vertices goes down exponentially, and therefore the number of rounds required is post log n. So we also look at the space that is required to count the triangles. And it should be clear to see that since the vertices that are being deleted and the ones that we're looking for triangles for have degree at most alpha, we can use at most alpha squared space in order to count the triangles adjacent to them. So no machine actually needs to have more than alpha squared space to naively count the triangles. And finally, we note that the total space that is used by the algorithm only has an overhead of alpha over the number of edges, because again, if you look at the counting of the triangles, of course, like we are making, if we do the naive thing where we look at each green vertex and try to look for all pairs of neighbors that are next to each other, we can instead look at it from the perspective of each edge, and each edge that is involved in such a procedure is only duplicated at most alpha times, because the vertex corresponding to that edge that is being deleted has degree at most alpha. So basically we obtain a space overhead of at most alpha, and that gives us the simple algorithm based on Chibi and Shisaki, which gives us an M alpha total space log n Brown's algorithm. So now let's look at our algorithm, which is sort of a modification, where instead of using the same threshold at every round, we use an adaptive threshold, where the degree by which we delete vertices at round I depends doubly exponentially on the round number. So in the first round, it sort of looks the same, where you delete all vertices that are less than 4 alpha degree, and you sort of update the count with however many triangles you found. However, the next round, we can up the threshold, and intuitively, this is because since the size of the graph is decreasing, we can be a little bit more aggressive with the size of vertices that we're allowed to choose, and it'll become clear how we deal with the larger degrees as we move forwards. But we can use this new threshold to then again count the triangles, update the count, and we can do this until we basically run out of the entire graph. And the number of rounds, which is basically the max round number until we run out of all vertices. And since the max value of the round number depends, or rather the degree of the vertices being removed depends doubly exponentially on the round number, the max round number is going to be at most log n. And this is an exponential improvement over the previous algorithm. So let's look at the sort of size reduction in the graph as we proceed through this algorithm. So let's assume that the number of vertices left after the first round is something like x. And first, we do something similar to the old analysis, where we upper bound this x by the number of initial edges in the graph, because remember that everything that remains has a degree that is at least 4 alpha, and therefore, like, we can upper bound this by the total number of edges in the graph, because the total number of edges cannot be smaller than the total number of edges just contributed by the remaining vertices. In the other direction, since the final graph, so the number of edges in the final graph being M1, since the final graph also has a bounded arboricity alpha, we can simply bound lower bound x using M1, because M1 covers at most alpha forests that are situated on those x vertices. So given both this upper and lower bound, we can then bound M1 in terms of M, and we notice that the number of remaining edges is at most half of the initial number of edges. So we can take this analysis in the general setting, or for a arbitrary round number I, and we can basically take Mi minus 1, which is the number of edges remaining at the end of round I minus 1, and compare that to Mi, which is the number of edges remaining one round later at round I. And we get sort of this relation that depends, instead of just being divided by 2, we get a relation where it depends, that the discrepancy between round I and round I minus 1 is roughly off by a factor that is proportional to the threshold used at that particular round. And essentially, inductively, we can show that, therefore, Mi, the number of edges remaining after I rounds, actually decreases doubly exponentially with respect to the original number of edges in the graph. So given that, since we know that Mi is decreasing doubly exponentially at the same rate as the degree threshold is increasing, we can then bound the total memory required. Because the total memory required is, again, this doubly exponential quantity multiplied by the arboricity, but the number of edges has reduced so much, when we multiply those two together, the doubly exponential part cancels out, and therefore we are again left with only an alpha overhead in the total number of edges that have to be considered by the algorithm when we look for the triangles. So one challenge is that the next part of this, where we sort of bound the space that is required to count the triangles, we can no longer do this with the small alpha squared space because we in general cannot even count the triangles on one machine because the degrees can be arbitrarily large in this case, since they're not restricted to just O of alpha, they're growing exponentially. And the solution is essentially to use sort of a distributed algorithm across multiple machines where the counting of triangles is reduced to several primitives that basically work by merging, sorting, and finding duplicates in lists. So the simple algorithm sort of goes as follows. Every removed vertex, so one of those green vertices that got removed, sends a neighbor list to all of its neighbors. Then every vertex that receives the neighbor lists, merge those received lists with its own adjacency list. And finally, if you find any duplicates, that means that you shared a neighbor with your vertex, and that indicates a potential triangle. There's obviously going to be some overcounting here, but that's easy to take care of because every triangle will be counted from each of its endpoints. So let's look at an example here where the vertex C is going to look at its neighbor list and send its neighbor list to all of its neighbors. Let's focus on one of them, D. And D receives the neighbor list of C, which is A, B, and D, and merges that neighbor list with its own neighbor list, which is B and C, and finds a duplicate. And the duplicate essentially indicates that C and D both share a common neighbor B, and that basically is how a triangle is detected in the graph. So the primitives we use to actually implement this involve sorting, and also a new primitive for finding duplicates in merged lists. And sort of roughly how that goes is as follows. If you have like various lists that you're trying to merge, and note that these lists can be of size that are larger than the machine, so these might actually be split up across various machines. We can sort of use the sort of interval tree structure where we merge the list one by one, or in pairs, and we get like sort of, instead of just a list of elements, we sort of assign them with counts. So this sort of diagram indicates how we can then merge those counts into a unique counts list and sort of proceed to the next level. And once that happens, we can find the duplicates where, because of the binary tree structure of this procedure, we use a number of rounds that is log of n to the base the space used by each machine, which ends up being just a constant number of rounds. Next, we consider the approximate triangle counting algorithm, which uses near linear memory, total space, which is actually tight to the size of the input, and produces a 1 plus x approximation, given the caveat that the number of triangles is at least the square root of the average degree. This lower bound should sort of make sense in the sense that we're looking for a multiplicative approximation based on a sampling algorithm, and essentially if there are too few triangles in the graph, the sampling algorithm might just not see any of them, so distinguishing between 0 and 1 triangles ends up being very difficult. So as long as you have a certain number of triangles, this algorithm will still give you a good approximation multiplicatively. This compares to existing work in the same domain where we can see that our lower bound for the number of triangles is actually a lot better since we get square root of d average. However, the total space we used has some additional polylog factors that previous work did not require. Additionally, our space for a machine is worse than the ones in SPK13, and compared to PT12, we notice that in some regimes we actually do better than them in space per machine. In some regimes we do worse, depending on this quantity that depends on both the number of triangles in the graph T, but also the max number of triangles on any edge in the graph, which is the delta E quantity. So depending on the graph structure, we might do better or worse than them in terms of space per machine. The main advantage of the sampling-based algorithm is that it's fast and it uses less total space. But the main disadvantages are that we require this lower bound in the number of triangles, and we also require higher space with plus machine, pushing us into the linear memory regime. So let's look at the algorithm. Essentially what we do is we take the input graph and sort of the high level structure, even though we can't do this on one machine, is that we take each vertex and assign it to every machine with probability p, independently and uniformly at random. And once that happens, we actually compute the induced subgraph on each of these machines and count the number of triangles in the induced subgraph. So each machine gets a collection of vertices, each landing up in the machine with probability p. The induced subgraph is computed, and then the number of triangles are counted. And basically this gives us an unbiased estimator that's sort of scaled by a factor of p cubed for the number of triangles in the whole graph, and basically repeat this experiment a bunch of times, aggregate the results, and that gives us an estimate for the number of triangles in the original graph. The challenges are as follows. First of all, you have to make sure that the induced subgraphs do not exceed the space per machine. And essentially, this happens by choosing the parameter p carefully so we don't end up with too many edges landing up on a single machine. And we also have to make sure that this bound holds in high enough probability that none of the machines end up overflowing, or even if some of them overflow, it does not affect the aggregate significantly. The more interesting challenge is how we compute the induced subgraph for each machine, because even though the vertices get assigned, even after the vertices get assigned randomly, the edges between them are not determined unless you want to query each pair individually, which obviously will take too many queries and too much space. And in this setting, we can't really partition the graph since we're actually sending vertices randomly. A single vertex might end up in multiple machines. So instead of doing this directly, what we do is we relax the requirement for the assignment of vertices to machines to use a k-wise independent hash function instead of a fully independent process that truly uniformly randomly assigns the vertices to machines. And by using this k-wise independent hash function, this actually allows each edge to determine by itself which machines it ends up in by using the hash function on both of its endpoints. And that allows us to, in a small amount of space, assign all the appropriate vertices, all the appropriate edges to all the machines and obtain the induced subgraphs. And finally, we have to make sure that the number of triangles actually concentrates across all the machines, or rather the aggregate of the number of triangles concentrates. And this can be done by ensuring that there's a constant probability of success and sort of using the standard median trick to amplify that. So that's sort of like the high-level overview of the approximate counting algorithm. I'll leave this talk with some open questions. A simple open question, and an obvious one, is that whether we can count a broader class of subgraphs. So we investigated several 5-node subgraphs and larger cliques, but potentially there's other graphs that can be counted. So for instance, there's some recent work which uses DAG tree decompositions in order to count subgraphs, and potentially these techniques can be implemented in MPC, resulting in a different family of subgraphs that can be counted efficiently. We can also consider whether these algorithms can be used in the AMPC or the adaptive MPC model, which is essentially MPC augmented with a distributed hash table, which allows the machine's additional power to query into the previous round of communication in a random access fashion. And potentially in this model, we can obtain much more efficient algorithms for counting subgraphs. And finally, interesting open question would be to approximately count triangles in a constant number of rounds, but use strictly sublinear space instead of the O of n space that we obtained. And this would be particularly interesting when the number of edges in the graph is very small, so in a sparse graph where m is O of n. So that concludes the talk. Thank you for your attention.